length around this circle, then what we can do is imagine we have a tangent vector like that, right? And then what we can do is we can scale it back. So that is the magnitude of r prime, right? The length of that is magnitude of r prime. And then I multiply it by dt, which is an infinitesimal, which scales it. dt is like a number. So what I do is I get like this little infinitesimal little piece of the arc. And then I do the integral, and that adds up all those little infinitesimal tangents all the way around. And you get the length around the curve, if that makes sense. We won't get into the actual formula, okay, because it gets a little complicated. But if you can take that on faith, that it makes sense that we're just adding up a bunch of little infinitesimal tangents, then that's going to give us the arc length. All right, so what is the arc length of this? What's the arc length without even doing a computation at all? 1. Close.
Oh, 2.
What is that drawing? Unit circle, right? So I want the arc length, which is the same as circumference, right? What's circumference of a circle that has a radius of 1? 2 pi. Well, 2 pi times r, and r is 1, right? Our answer should be 2 pi here, shouldn't it? Should be. Okay, so let's do it. Let's find the derivative. What's r prime of t? We've done this. Right? Now, what's the magnitude of this? Square root of that squared. Doesn't matter that it's negative, right? Because I'm squaring it. Plus that squared. Beautiful. That's Pythagorean identity. That's just 1, right? That's all it is. So now we set up the integral. The arc length should be the integral. Now we need our time restriction. T is going to start where and end where? 0, 2 pi. And we're integrating what? 1 with respect to t. So the antiderivative of 1 with respect to t is t, right? And we're evaluating 0 and 2 pi. 2 pi goes in, you get 2 pi. Subtract, plug in 0, you get 0, and your answer is 2 pi. That's it. That confirms what we kind of knew to start, right? Out of curiosity, what if I wanted to prove to somebody that the circumference of any circle, radius r, is 2 pi r? What could I do to modify the problem to make this a general answer? How do I change that circle from a unit radius to a radius r? Yeah, why don't I just throw an r right there and an r right there, not to be confused with that r. Okay, so r is a constant. It stands for our radius. If you want capital R, how about that? Capital R, capital R. Wouldn't that draw me a circle of radius capital R? Okay, so what would happen in this? I would take the derivative. The r would just come for the ride, capital R, right? And when I squared each one, the negative wouldn't matter, but I would have capital R squared here and capital R squared there, right? I could pull the capital R squared out of both and then pull it out of the root. And I'd still have a 1 there. So this would just turn into the r, and then this would just be r. All right? Now I integrate, and r as a constant can come out. And I still get the same thing, r, and then this just has an r, and everything just turns out the way we would think. Okay. I feel like I'm going too fast. Are y'all all right? Yeah, just remember, you got the video. If you need to come back, you can watch something. You know, don't necessarily worry too much about copying every little thing down. Yeah, who cares? All right, now, what about in 3D? Three-dimensional vector function. Same story. The only thing that changes, look, this is the exact same formula. Exactly the same. The only thing that changes when you do this, you have that extra component function in here, right? That's the only thing that changes. Everything else, just integration. So can we figure out the length of this curve? So check out this curve. This is that curve right there. I want to draw that red part of the curve right there. I want to know how long that is. So if you took this little spirally thing, took it off the page, and straightened it out, measured it, right? Then how long would it be, right? Seems like a reasonable question. By the way, if we look back at the vector function, the first two components are cosine t, sine t. We already know that drew a circle, right? And then the z component is t. And we talked about this. This is that, yeah, this is like if you look at it from the top down, right? You've got your x and y, and the z's going into the page. Then, you know, if you're just looking from the top down, it looks like you're just drawing circles. What you can't tell is that it's coming out towards you, right? And that's what the z component is forcing it up as you draw the circles. All right, let's find the length of this curve from the point 1, 1, 0 to the point -1, 0 pi. So I'm going to need the derivative, right? Derivative is negative sine t, cosine t, and 1. Yes? And we need its magnitude. Square root of sine squared t plus cosine squared t. That's going to be 1 plus 1. So that's root 2, isn't it? Root 2? Yeah. Okay, so I'm going to now integrate root 2 dt. And I could pull the root 2 out or just leave it in there. But what are my limits of integration?
0 and pi.
Okay, so where's that coming from? Where's 0 pi coming from?
Z component of the point.
Yeah, you have to figure out, what does t need to be to give me that point, and what does t need to be to give me that point. And this will correspond to a and b on our limits of integration. So again, this function is easy to look at and tell, right? Because I gave you the last component is t, right? So if you want that last thing to match, then this had to have been 0. And then this last component, or point has to match the coordinate, has to match that component. So t would have to go to pi. Make sense? Yeah, I don't know why I put t. That should have been pi. So we're going to go 0 to pi. And then you could do that, right? All right? Questions? Yes,
Yeah,
thank you.
Could you explain real quick how you got A and B?
Okay, so this draws a curve, right?
Yes.
And I want to start at this point. So the question becomes, what t do I plug in here, here, and here to give me 1, 0, 0?
Oh.
Right?
Oh, and T is 0.
And you can just see it matches, exactly. Now, this would be a more difficult problem if this wasn't t. If this was like maybe, I don't know, square root of t squared minus 1 or something like that, where you'd have to actually try and get them all to match, then, I don't know, that's probably more like what you'll see on your homework, is something more difficult to match. But it can be done. How about this one? This one, I think the derivative is a little more involved, right? So what's the derivative of this? 3t to the half. Okay, and then this derivative of this?
-2 sine 2t.
-2 sine 2t, and derivative of this? No, you're good.
Oh, yeah. Okay.
You're good.
2 cosine.
And then 2 cosine 2t. Okay, that's your derivative. And now you need the magnitude of it, right? So the magnitude is the square root of, let's see, square this and you get 9. And then that means square root, right? So 9t. Now be careful here. Squaring this, you get plus 4 sine squared 2t. And then squaring that one, you get plus 4 cosine squared 2t, right? Which is square root of 9t plus 4. You just factor 4, just ignore that. Factor 4 out of both of those and you'll get a Pythagorean identity. And that just becomes a 4. So that's what I need to integrate, right? I need to integrate that from where to where? 0 to 1. And this one, they actually gave me the interval. They gave me the t where I start and the t where I stop. See the difference? If they give you the interval, it's easy. If they give you 2 points, you have to extract what t is. And I'm integrating root 9t plus 4 dt. And how would I integrate that?
Plug in your t value.
What do you mean?
Right.
U sub.
This is basic u sub. The basic u sub would be 9t plus 4, and then the derivative of that. And now if this was 9t squared plus 4, now you're looking at like trigonometric substitution. Trig sub, Cal 2? Remember that?
The triangle.
Yeah, reference triangle and all that. But it's not t squared. You get the idea though? I'm not going to take it the rest of the way. You just do your integration on that. So you could probably have a lot of different things show up, right? As you might imagine. All right, now we move on to this idea of curvature. Curvature. The curvature of a vector function is a number. Good, it's just a number, all right? Which represents how quickly a curve changes direction at a given point. And the curvature can be found by computing one of these two formulas. There's actually two formulas for curvature. The first one is the, capital T. What was capital T of t without the derivative? What was capital T of t? The unit tangent vector, right? So if you calculate the unit tangent vector, then take its derivative, then take its magnitude, and divide it by the derivative of the vector function, its magnitude, that will give you the curvature. Or if you don't like that, you can do this formula instead, where you take the first derivative of the vector function, cross it with the second derivative, take the magnitude, and then divide it by the first derivative's magnitude cubed. They're both don't look fun, right? Now, I do say here that this is only good in three-dimensional space, and that's because our cross product is only defined in three-dimensional space. Although there are workarounds for that, we can get around that, but just for now, let's say that's where we are. So sometimes this formula is better than this formula. It just depends on the problem. I can imagine right now we're going to do an example. Show that the curvature of a circle, of this draws a circle, right? Show that its curvature is constant. So would it make sense that it's constant? If you're drawing a circle, curvature is somehow measuring how fast the function is turning. So let's compute it. And I'll go back to the note so we have the two formulas here. There they are. And we have the vector function that we're working with here. R of t is cosine t sine t. So I'm going to use the first formula because this one only works in 3D, right? So I'm going to use the first one. So I need the derivative, don't I? So that is negative sine t cosine t. I've done that, what, at least 4 times now? Okay. What is capital T of t? Because I need the derivative of capital T of t. So what is capital T of t? By definition, it is r prime of t over the magnitude of the derivative. That's the definition of capital T of t. It's the derivative of the vector function over its own length, which is negative sine t cosine t. That's r prime of t, right? Over, what's the length? What's the length of this thing? Square root of that square plus that square, Pythagorean identity again? You're going to get 1. So this is just negative sine t cosine t. Are you with me? Okay. Now, the top of this, the curvature, right, is the derivative of that. Magnitude. So let's take its derivative. What's the derivative of this? Derivative of this is negative cosine t, sine t, negative sine t. Right? Negative cosine t, negative sine t. That's the derivative of that. And now we need its magnitude. So the magnitude of the derivative is, well, 1 again, right? Okay, all of that for 1, right? Now we need to divide that by what? The magnitude of r prime of t. Now I never did that, so magnitude of r prime of t, but that is what? Yeah, it's just the magnitude of this, which again, we Pythagorean on that, that's going to be 1. And so you do 1 over 1, you get 1. So the curvature is 1, it's constant, isn't it? Okay, not bad. Now, can I show you how we could use this formula? Can I just show it to you? Even though it's a two-dimensional vector, we can still do that. And here's how we do it. We take the original vector function that's two-dimensional, and we add the third dimension, and we just put 0 there. And that means it's going to draw a curve in three-dimensional space, but there won't be a z component, which means it'll be on the xy plane. And so it's two-dimensional, but it's really three-dimensional. But it allows me to get around and still do cross products. All right, so let's do I'm going to do this formula right here. So I have the original vector function. It's now been moved into three-dimensional space. I'm going to take its derivative, which is still this, but with a 0. And don't I need another derivative? So double prime of t, right? Second derivative we need in there. So take derivative again, we got negative cosine t, negative sine t, 0 again. Yeah? Now we need to do the cross product of those two, which is these two, right? Let's cross them. So this is that thing that we did before, right? Cover this up. Here, here. Oh, that's nice, isn't it? Here, here, 0. So my cross product, r prime t crossed with r double prime t equals, the first component was 0, right? Okay, now cover up the middle one. 0 again. This is nice. And then cover up the last one. Sine squared t minus negative cosine squared t, which is the same as sine squared t plus cosine squared t, which is 1. So Pythagorean helped us again, right? And then we need its what? Its magnitude. And what's the magnitude of that vector? 1. So we take the magnitude of that, and we get 1. Okay, so the numerator is 1. Now the denominator is r prime of t magnitude cubed. R prime of t, take its magnitude, squared, 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 added together, square root, 1 again, right? So that turns out to be 1. And then cube it, it's 1. So we get 1 over 1. Right? I just wanted you to see how you could move a vector function from 2D to 3D if you needed to. So look at this. As I move through here, as I move around, I'm having my computer calculate the curvature, and notice it's not changing. Now, compare that to this one. So I'm at t equals 0 right now. I'll show you the vector function in a second, but look at that vector function. It's definitely not drawing a circle, right? So look at my curvature right at the beginning. Look at my curvature. Let me slow this sucker down. Right at the beginning, I can't do that. The beginning, my curvature is really big, right? And watch what's happening. It's hard to see. There's some very tight spirals down in there you can't see. But what's happening to my curvature here? It's getting smaller and smaller. Isn't it? So like very tight curves. And then as you go out, almost like G-forces if you want. You know, it's kind of really tight and then it starts to spread out. Now we got, you know, these curvatures of decimal, like 0.08. And it's actually going to go out and get really small. It's actually going to have a limit, right? The limit's going to be 0. As t goes to infinity, the curvature looks like it's going to 0, which means it's basically headed to a straight line. Doesn't that kind of make sense? As this thing gets wide enough, it's almost like you're traveling in a straight line. The curve is so big. Now, what function was that? Oh, I didn't put it up here. Oh, here it is. It's this right here. It's basically like t cubed cosine 10t, t cubed sine 10t. But that was just to illustrate an example. Let me see where we are here. I'm going to leave this to you, right here. And I mean, your homework is similar to this anyway, but I think this is going to be a little bit problematic as you're going to go through it and see that you might work through this one and decide to change your formula midway. You may be like, oh, shoot, I do not want to do that. Okay? Like you'll see the algebra, like there's two formulas, right? You'll start working one of them, you'll be like, ooh, the algebra there is really bad. So you switch to the other one, it works out a lot better. So sometimes you don't have a choice. The function itself dictates which formula to use. But the good news is it's in three-dimensional space. So you don't have to like extend it out from 2D to 3D. And that is it. And on the homework, just make sure you notice that on 11 through 14, I just want you to find capital T. I don't know if that's in the schedule, if it says that. It does say that? Yeah, it does. Find capital T. All right. All right, we got 20 minutes. Let's keep going. Is that it? Are we done with 11 or chapter 10? Yeah, we're done with chapter 10. Double check. There is another section in here, 10.9, and it's actually a really good section. Motion in space, velocity and acceleration. So it goes more into detail with the concept that we just had of, you know, take the derivative and you have velocity, second derivative, you got acceleration, that thing. But because of time and because we do want to get through this book, we proceed into chapter 11. Now, chapter 11, chapter 10 was called Vectors in the Geometry of Space. So everything we're doing in chapter 10 had to do with vectors and all the different sort of geometry that we had. Now, chapter 11 is called Partial Derivatives. And we are going to, for the time, we are going to kind of put vectors away for a little bit. All right? So please realize that we're shifting gears. The first section in chapter 11 is called Functions of Several Variables. So things that we've already seen is that anytime we have an equation that has x, y, and z in it, that it gave us a surface. We did all those cones and paraboloids and all that stuff, right? And we looked at the differences in the equations. We know that a plane, flat sheet of paper, has x, y, and z in it, right? So we already know that. The question becomes, or the statement I should say, is that if it is possible to isolate or solve for z in one of those equations, then z can be seen as a function of two variables x and y. And we can then write z as being a function of x and y. So this is kind of like back in college algebra when you have something like x minus 4y equals 8, and you say, okay, yes, that's a line, right? But then you would solve it for y. So you'd move things around, solve for y, divide by 4. And then you say, now y depends on x, right? You give me x, I have y. So we could say then that y is some function of x, which is 1/4 x minus 2. So y depends on x. Same exact principle. if we have an equation that has x, y's, and z's in it, if we can solve for z and get the x's and y's on the other side of the equation, then z depends on two things, x and y. You give me x and y, I give you z, right? And so we look at z as being a function here of two variables, right? Two variables. Questions on that? I should also illustrate to you that when it came to graphing, when we had this thing right here, y is equal to some function of x, which is 1/4 x minus, I forgot what it was, 2, whatever. When we graphed that, when we wanted to get a visual idea of what this looked like, what we did is we said, okay, oh, let me do it this way. We said to ourselves, look, we have input, goes through the function f, and we have output, right? That's the idea of the function. The input in this case was x, right? Which was just a number. That's a number. And then it got sent through the function and it spit out a number, right? So number in, number out. Number in, number out. So we said, okay, numbers lie on number lines. So what I'm going to do is I'm going to draw a number line, and that's going to be my inputs. And then I'm going to draw another number line for the outputs. And I'm going to draw it like this. These are my outs. And so we looked at the input. Let's say we had a function like here. If I plug 4 in, where does it go? -1, right? So we could visualize that by saying if I go out to 4, right, then it spits out 1. And that point is a visual representation of this relationship, right? And if we put them all together, then all the different answers would draw that line, correct? But we said number in, number out. When we look at this, we have two numbers going in, right? And one number coming out. So what's that mean? What's that mean? With this notation, it's important to see that the domain of the function, the inputs, are ordered pairs as opposed to numbers. They're ordered pairs going in. They get plugged into the function. This means our domain is two-dimensional because an ordered pair requires 2 dimensions. So instead of us having a number getting sent to a number, we have a point in space getting sent to a number, don't we? And because we have that, if we want to visualize this, we're going to need 2 dimensions to represent our input and an additional dimension to represent our output. 2 dimensions, 1 dimension, we need 3 dimensions to visualize this. So here we can just practice, you know, looking at a function of 2 variables and plugging numbers in. Like if I gave you this function, this is really like saying z equals f of x, y. There it is. So find f of 2, 1. So you're going to replace what with 2 and what with 1? The x is 2 and the y is 1. The order matters, right? 2, 1 is different than 1, 2. So real quick, what would that be? Square root of, see on top we're doing 2, 1, so 4 on top. So root 2 over root, hold on. 2, let me do a little slower, plus 1, plus 1. That's plugging in the top, right? Over what? 2 minus 3, so 2 minus 3 is -1. So what would we have? 2 over -1, so -2? Right, that's what we get if we plugged in 2, 1. How about 0, 0? We get something else? We get 1 over -3. What about -4, 1? Yeah, if we do that, we go -4 plus 1 over -4 minus 3. What happens there? We get a negative underneath the root, right? Which we can't do, right? So there are some domain problems here. We have domain problems. So we have to actually think about what we can and cannot plug in. So let's talk about the domain. Can somebody tell me, like, just right off the bat, what we cannot have?
Cannot be
X cannot be 3, right? Does everyone agree with that? X cannot be 3. Okay? So when I'm talking about domain, I'm talking about that stuff in two-dimensional space, right? And we already know that x can't be 3. So x is 3. There's 3, right? On x, I can't pull any ordered pairs off that line. Off that entire line, right? Any point that lives on this vertical line has an x coordinate of 3, and that cannot be in my domain. Right? Okay, that's one problem. What's the other problem? X plus y plus 1 must be greater than or equal to 0. Because what's underneath the radical cannot be negative. Right? And this, back in some other class you took, is called a linear inequality. Linear inequality. And the way you solve these is, well, you turn it into an equals first. So if you don't remember this, just say linear inequality and then go have fun on YouTube. You turn it into an equal sign first. Then you solve for y. Right, like that. Okay? And then you graph the line. And that line you should be able to graph. Y-intercept of -1, slope of -1. So down 1, like here, and then it goes like this, right? So do I want to include the line in my answer?
Yes.
Yes, why?
Because
Because it's equal to 0. So it's okay to be equal to 0, so it's okay for this to be equal to 0. So I want to include my line, like this. Now, do you remember this part about linear inequalities? You then have to shade either the top or the bottom of this line. It's either going to be all the points above it or below it. So how do you figure out if it's above or below? There's a real easy way to do it. Just pick a test point. Just pick a point either above or below the line. So I like to pick the easiest point I can find if it's available. I like this point 0, 0. And I'm going to check, does that work or not? And I'm going to check it into here. Not into here, into here. So if I plug 0 here, 0 here, is that true?
Yes.
Should be, right? That's going to be 1 is bigger than or equal to 0. That works. So if that point works, it means everything on that side of the line works. What if that point didn't work? Then it's everything on the other side of the line. So I know it's everything over here, right? Except for this, right? So we have to combine the two together into some sort of like final answer. So we would say something like, or if we drew it, I want you to be able to draw it. It would be something like this. Our domain would be everything like this, and then we would have a hole here like that. And let's say this is 3 here. Okay, and then it would be all this stuff over here, all this stuff over here. Does that make sense? Now, algebraically, the way you could say the domain is this and this. That's the algebraic way you could say domain. It's all the x's, so long as x is not 3, and at the same time, this has to be satisfied. But you should be able to draw the picture of it. Would y'all like to see this function? So what happens here, go back to the beginning here. Just remember what's going to happen. Is that now the xy plane, which in this classroom we said is the ground, right? The xy plane is now our input, and the output is just how high off the plane you want me to go. So for every ordered pair that we pick for a function of 2 variables, what we're going to do is we're just going to pick some points and start throwing them into the function. This is just kind of give you an idea. Like I'm picking some points on the xy plane, I'm throwing it into some function. This is not the function we just looked at, okay? This is just to make sure we understand how this is going to work. We start plugging more and more points in, and in 2-dimensional space we eventually draw a line, but in 3-dimensional space you start plugging all those points in, then you start to get, you know, some sort of surface at some point, okay? Okay, so let me get this all out of here. This is just more of the same. Jeez. I think y'all understand it. I kind of went overkill here. We're picking something in the domain, and then it's, where the hell's the point? Where are you? Oh, I'm not showing the point. Duh. There it is. Okay, so we pick some point in the domain, and it gets spit out somewhere on our surface. Y'all are getting this or not? I don't want to treat you like children here. Yes, you get it? Okay, so we're going to get some sort of surface. Now, here's that problem that we just had, right? We just found the domain of it?
Yeah.
This is the graph. That's the graph of that surface. What's really cool is if you look at it from the top, what does that look like? That's our domain, right? We said everything above that line, and we said everything except 3. But when we pop it out of there and just try to look at it from this perspective, right, we can see we have something happening there. We have like a vertical asymptote, don't we? We have almost like a rational function is behaving almost like a rational function behaves. Kind of cool, right? So what about this one? This is another example. I've got to get the sign-in sheet going around. For this one, what can I not have here? Can you tell by the domain? Just sign in for last week if you didn't sign in or whatever. Yeah, so the only issue we have here is that this right here is inside of a natural log function, and you cannot plug in 0 or negative numbers into natural log. So we have to have that y squared minus x is greater than 0, right? Strictly greater. And this is a, what type of inequality is this? It's not a linear inequality like the last one. It's a quadratic inequality. And how do we solve quadratic inequalities? Oh, well, we first turn it into an equation. Okay? And then we move the x over, and then we ask ourselves, do we know what that looks like? And hopefully we know what that looks like. Parabola, but it opens up sideways like this. And so it should be a parabola like that, right? Now, do I want to include the parabola? No. I don't want the parabola included because we have to be strictly greater than 0, and this is what's happening at 0. So we don't want the parabola included. And then again, it's kind of like, well, do we include the stuff in here or the stuff out here? So you do like another test point. So what could I pick? What's a good test point? I can't pick 0, 0 because 0, 0 is right there. 2, 0? And then just check it. Does 2, 0 work here? 2 for x, right? 0 for y. Does it work? No, it does not work. Which means that we are like this. So when I graph this thing, when I look at the picture, there should only be a picture above here. Right? When I graph it, it should only be above that. Does that make sense?
I was going to say the negative wasn't included, though, right?
What negative?
The parabola.
Anything on this side of the parabola is good.
The parabola itself.
The parabola itself is not included. Because if I pick any point on the parabola, it satisfies this equation, right?
Right.
And that makes it 0, but you can't plug 0 into the natural log. So you cannot include the boundary of the parabola. In the picture of this one, there's the picture from the top. Okay, so that's the surface from the top. And then pop it out of here. Let me pop this out into 3D. See it? Get an idea? So if I turn it this way, you see that was our, this is not working. Stop. Let me just go top. There we go. That was our x and our y, right? This is just the computer having trouble, okay? This is the computer going, oh crap, I don't know what to do, I'm getting weird stuff. So it's just kind of jaggedy. But there is kind of like an asymptote around the boundary of the parabola. It's like falling off into the abyss. Yes?
So is the outside like continuing infinitely, or is that actually?
Yes, it's continuing, yes.
Okay.
So the parabola keeps coming this way, right? And this keeps going. I just, at some point, have to stop drawing the surface.
Okay. Just
Yeah.
checking.
Is that sign-in sheet getting around? Look at this one. I know we're running out of time, but basically you would have to take that and make sure it's greater than or equal to 0. And if you do that, you wind up getting another quadratic inequality. And it turns out that it will become a circle. And so what you have is a little circle from the top, and then on the bottom, I'm sorry, not the bottom, you just have this little top of a ball, basically, almost, for this one. Okay, yeah, that's a good place to stop. All right, I know we moved kind of quick today. I hope that that was an okay speed. There's a lot to do.